Welcome to lecture 7.5. So here we have example 1. Solve the equation for x in the interval 0 to pi. Okay, so since we're given a specified interval, we don't have to worry about adding on 2 pi k or something like that to our answers. We can just have some specific answers. So let's take a look at what we have here. 4 cosine squared x equals 3. So I want to get cosine by itself, so go ahead and divide both sides by 4. And then I have cosine squared x equals 3 divided by 4. Let's go ahead and get rid of that square. Square rooting both sides. Remember the plus or minus. And then we get cosine of x equals plus or minus root 3 over 2. Okay, so we have two different answers for this. So where is cosine equal to root 3 over 2? Let's go ahead and take a look at the unit circle. Cosine is positive root 3 over 2 at pi over 6 and at 11 pi over 6. That's where cosine is positive root 3 over 2. Now, when is cosine the negative root 3 over 2? It's negative root 3 over 2 at 5 pi over 6 and at 7 pi over 6. Okay, so this is the main unit circle, and where are we looking at? We're looking at the interval from 0 to pi. So within this interval, what are our two solutions? Well, the two solutions here are x equals pi over 6 and x equals 5 pi over 6, and that is where our solution is. Once again, if we did not have an interval, we would have to do something like pi over 6 plus some version of pi. But since we're given an interval, we can go ahead and give our exact answers. Alright, so example 2, solve the equation. Okay, so what should we do here? We have cosine on one side and sine on the other side. The easiest method to do is we're going to go ahead and set our equation to 0. Okay, let's go ahead and do that. So subtracting everything else to one side, we get 2 cosine squared x plus sine x minus 1 equals 0. Now, what can we do here? Well, I'm going to think of any of the identity properties that I know to simplify with. Well, I do know that cosine squared x is the same as 1 minus sine squared x. And if I substituted that in for cosine squared x, I could have one equation in just one trig term, or sorry, one trig function. So let's go ahead and do that. If we can simplify to get just one trig function, that will help us. So we'll go ahead and plug that in, replacing cosine squared with 1 minus sine squared x. Once again, trying to simplify by only having one of the trig functions in our equation. And then we'll distribute that 2. And what do we have? We have 2 minus 2 sine squared x plus sine x minus 1 equals 0. Okay, so let's go ahead and combine the like terms of that 2 and that negative 1. And what do we get when we have that? So we'll have the negative 2 sine squared x plus sine x plus 1 equals 0. Now this is starting to look a little quadratic to me. See, we have the squared version of sine. We have sine squared and then sine not squared. So this is looking quadratic. And what we do with quadratic equations is we try to make sure our squared term is not negative. So we're going to go ahead, multiply both sides of our equation by negative 1, and we'll end up with that positive for our squared value. The next thing, once we have something that looks similar to being quadratic, and once again, how did I think that, or why did I think that? It's because we had a squared version of sine and a non-squared version of sine. So we could try and simplify this. I'm going to go ahead and try using a u substitution. So I'm going to say let u equal sine of x. Let's see if we can simplify anything. So that means I'm going to have 2 times u squared plus u minus 1 equals 0. Is this easier to solve? It is. I know how to factor that. That would factor into 2u plus 1 times u minus 1. Oh, I just realized that should be a negative right there. when we divide by the -1, that should become a negative, and that should become a negative. Okay, then it does factor. All right, so we have that equal to 0. And then with the zero factor property, set each term to 0 and solve. So we have 2u plus 1 equals 0, and then u minus 1 equals 0. Then we get u equals 1, and u equals -1 divided by 2. Okay, but we're not done. Remember, we're trying to solve for sine. So we're going to go ahead and resub this in for sine. And we have sine of x equals -1/2, and sine x equals 1. Okay, so the u sub really helped, and how did I know to use it? Because it was starting to look slightly quadratic. We had the squared version of sine and the non-squared version. All right, so now we're trying to solve this. Do we have a boundary? No, we don't. There is no boundary. So where is sine equal to 1/2 and sine equal to 1? Let's go ahead and work with the 1. So when sine is equal to 1, at right here, pi over 2, and that is it. That is the only place that sine is equal to 1. So where is sine equal to -1/2? Sine is equal to -1/2 down here at pi over 6, 7 pi over 6, and then down over here at 11 pi over 6. Okay, so that's where sine is equal to -1/2. All right, and once again, since we're not given an interval to answer, and we're going to have to go ahead and answer to include any of the possible versions for these. So with pi over 2, I would have to go one whole complete circle, so 2 pi, to get back to the next version of pi over 2, which means for that version of the answer, x is going to equal pi over 2 plus 2, and usually the book uses k pi. So k is some random number multiple of 2 pi. Could be 1, 2, 3, and so on. Okay, so we did that. That is a generic version for those answers. Now let's take a look at the next one. So the 7 pi over 6 and the 11 pi over 6. Well, if I can, I would really like to see if I could just use one of these and then add the 2 pi to it. But I don't really know how to get a nice even interval between these two. So I'm not going to do that. I'm just going to go ahead and add the 2 pi to 7 pi, because once I do that, we could end up right back at the next multiple of 7 pi over 6, and I'll do the same thing for 11 pi over 6. Just add 2 pi to it, a multiple of that, and we'll end up with those versions as well. And then we get x equals, so I said 7 pi over 6, and we had to do 2k pi to end up back to it, and also the 11 pi over 6 plus some multiples of that. And once again, we answer with the multiples of pi or 2 pi if we're not given an interval to answer in. Alright, so now we have example 3, solve the equation. Once again, we're not given an interval to answer in. So let's see. My plan is always to get it into one trigonometry, or one trig function. Right now we have tan and secant, so it's simpler if we can just get it into one trig function. I'm going to think back to my trig identities, or any of the trig formulas we have, and see if there's any connection between tangent and secant, so that I can sub one out for the other. And I do recall, for the identities, that tangent squared theta plus 1 is equal to secant squared theta. But I don't have a square for either of these. None of these are squared. That's a problem, but we can solve that problem. We could go ahead and square both sides of our equation. And then we would get the square. So when I square both sides, I'll get tangent squared of theta equals secant theta minus 1 squared. Alright, so then we have tangent squared theta equals, and once again, this is those two binomials being multiplied together. So we'll get tangent squared theta equals secant squared theta minus 2 secant theta plus 1. If you ever need any help on factoring or any reminders on that, I can go ahead and send you practice worksheets. Just let me know. Alright, so what I'm going to do, I want to write this in terms of one trig function, remember. So right now we still have tangent and secant. So I'm going to go ahead and solve for tangent here, so minusing the 1's on both sides. So then we have tangent squared theta equals secant squared theta minus 1. And now we can go ahead and substitute this in for tangent squared theta, and then we'll end up with only one trig function in our entire equation, which is awesome. We're closer to solving. I can see daylight. All right. Ooh, and look at this. The secant squareds are going to cancel each other out. So those are gone. And we just have -1 equals -2 secant theta plus 1. All right, so solving. Let's see. I'll go ahead and minus the 1 from both sides. And we'll get -2 equals -2 secant theta, dividing both sides by that -2. And we get secant theta equals 1. Now, secant theta equals 1. Now, we could try and answer it like this, but I'm not really certain when secant is equal to 1 on the unit circle. I know when cosine and sine are equal to 1 on the unit circle. Oh, you know what? Secant is the same thing as 1 over cosine. So when I do that, I might be able to find the answer for this on the unit circle. So then I have 1 over cosine theta equals 1, and then solving, so I can go ahead and do the cross multiplying. And I'll end up with cosine of theta equals 1. Okay, I know cosine theta equals 1. Where does it equal 1? So let me go ahead and draw my mini baby. Let's put this on the side. My minute baby unit circle right here. Cosine is equal to 1 right here at 0 or at 2 pi. We are not given an interval to answer in, so we'll have to go ahead and say theta is going to be equal to what? Well, theta will equal... Well, we only have one answer here. And to get to it again, we'll have to go around a whole 2 pi. So our answer is going to be 0 plus 2 multiples of pi. 0, 2k pi. Or we could simplify that answer into theta equals 2k pi. And there we go. So once again, how did we do this? Well, we started out with two different trig functions in one equation. We know that it's easier to work with just one trig function in an equation, so we tried to manipulate it to see if we could sub in an identity that we knew. Definitely keep the identities in mind when solving. Once we did that, this is a little hard to solve, so we decided to translate it into cosine, which we knew how to solve, and there we were. Alright, example 4. Solve the equation on the interval 0 to 2 pi. And notice we include 0, but we do not include 2 pi. So keep an eye on the parentheses. Alright, solving this. Well, in the beginning, there are two different trig functions in the equation. I'm going to go ahead and set this equal to 0 and see if I can get anything figured out. So cosine x sine x minus sine x. Well, I might be tempted to try sub something out, but I noticed before I try that, I have a sine in both terms. So I could factor sine out. Then I have cosine x minus 1 equals 0. So I could try and put one trig function into this equation, but I'm pretty much close to solving already, so I might not do that. Instead, I'll use the zero factor property and say that sine of x must equal 0, and cosine of x minus 1 must equal 0. Now go ahead and solve this, so cosine x equals 1, and look at that, we've already solved. So it was easier this time to notice that we could factor out factor out the function, instead of having to sub in some sort of identity equation. Alright, so we are given an interval, so let's go ahead and take a look. From 0 to 2 pi. And now we're looking at when sine is equal to 0, and sine is 0 at pi over 2. Oh no, sorry, not pi over 2. Sine is equal to 0 at 0 and 2 pi, as well as over here at pi. That's when sine is 0. Now cosine is 1 over here at 0 or 2 pi. So what would our answer be? Well, we're only looking at the interval from 0 to 2 pi. And in this case, we know that x for sine of 0 would be equal to 0 as well as pi, because those are both inside 0 and 2 pi. And then for the value here, we end up with that x equals 0. Now, why aren't we including 2 pi? It's because we're told not to include it in the beginning. So I'm not going to be redundant here with my 2x equals 0 value, so I'll go ahead and just erase that and leave 0 and pi as our two answers. Alright, example 5. Solve the equation for x in the interval 0 to pi, and we're including both 0 and pi. Okay, so the equation doesn't look too bad. We only have one trig function, which is cosine. However, there is something odd, which is that we have that 4 inside with the x. So that is in the function. That'll play an interesting part as we move along. But let's go ahead and just solve for cosine at the moment. So go divide both sides by 2. And we get cosine of 4x equals a half. So for now, we're going to go ahead and ignore the 4x, and we're going to just look at what we know. So we know that cosine of x equals a half at what values? At, let's see, we'll go ahead and draw that over here. Cosine is equal to a half at pi over 3 and also at 5 pi over 3. So that must then mean that the value on the inside, which we usually would say is x, so 4x must equal pi over 3, and we're going to go ahead and do the 2 pi to get back to our answer. And then we have the item inside our cosine, which happens to be this time 4x, is going to equal the pi over 3 plus however many intervals of pi we would need, so 2k pi. Alright, that was one of them. We still need to keep in mind that we have... Oh, no we don't. Actually, if you recall, we're just looking at the interval from 0 to pi, which means we don't have to look at this answer here. We'll just focus on that one. So we're almost done, except we're not actually solved for x yet, because notice we had that 4 times the x. So how do we get rid of that? We're going to go ahead and multiply both sides by a fourth. That'll cancel that x there, and we have x equals, well, when we distribute this fourth in, we'll end up with pi over 12 plus k pi divided by 2. Alright, so usually that would be the answer if we just had the x, but once again we had that 4x, so it changed our answer values from being pi over 3 to being pi over 12s. Okay, so because of that, we might actually have more solutions inside of our interval from 0 to pi. So the solutions that we would have, if we went ahead and just had 1 for k, that would be pi over 12 plus pi over 2, which would give me 7 pi over 12. So we can continue that, and we'll find our answers of x equals pi over 2, 7 pi over 12, 5 pi over 12, as well as 11 pi over 12 fit into our solution. Alright, so let's take a look at example 6. Solve the equation. Alright, so, well, it's all written in cosine and sine at the moment. So I guess I'd be tempted to try and use one of our identities or one of our formulas to solve this, because they both don't have a common factor inside each of these terms. So I can't factor something out. But you know, something that is suspicious is that this one term is cosine cosine, and then the second term is sine sine, and if you'll notice, there's a y and a y, and a 2y and a 2y. This looks an awful lot like the extension of our cosine s plus cosine t. So cosine s plus t, if you recall, equals cosine s cosine t minus sine s sine t. So we can go ahead and simplify this by identifying that the y value would be our s and the 2y would be our t. So rewriting this using one of our identities, we have that cosine y plus 2y equals 0. We just went the opposite direction and simplified. And then notice, y plus 2y, that equals 3y. So we have cosine of 3y equals 0. And once again, we've run into that weird instance where inside of our cosine function, we have a multiple of our variable. So first we're going to think about when cosine is equal to 0. So when is cosine of x equal to 0? Well, if we take a look at our usual unit circle, cosine of x is equal to 0 at 2 points, pi over 2 and 3 pi over 2. So we know that 3y must equal pi over 2 plus some multiples of that, so 2k pi, and that 3y must also equal the 3 pi over 2 plus some multiples of that, 2k pi. So again, as we did earlier, we're going to go ahead and just solve for y, because that's what we're trying to do. So multiply both sides by the third. Getting a little squishy here. And then we get y equals pi over 6 plus 2k pi over 3. And y equals 3 pi over 6, which we could simplify, plus 2k pi over 3. I'll go ahead and simplify that. So y equals pi over 2 plus 2k pi over 3. Alrighty, and since we don't have an interval in which to answer, we can just go ahead and leave our answers like this. A little simpler this time without that interval. Now, let's take a look at example 8. Solve the equation on the interval. Okay, so we're given an interval now, 0 to pi. We have cosine squared y plus 2 cosine y plus 1 equals 0. Now, when I'm looking at this one kind of just looks like a nice quadratic equation. What would make me think of that? Well, I have my cosine value and my cosine value, and then one of them is squared. So I'm going to go ahead and treat this like a quadratic, but I'll use a u sub to make it a little simpler. So let u equal cosine of y. Then we have u squared plus 2u plus 1 equals 0. Once again, u sub is something that we learn in Math 103 or 135, so if you've ever need a review on that, just let me know. Alright, so let's go back to solving this. So factoring, we'll have u plus 1 equals 0. Okay, well actually these are identical terms, so we have u plus 1 squared equals 0. Square rooting both sides. We'll end up with u plus 1 equals 0. So subtracting 1 from both sides, we get u equals negative 1. Then resubstituting our cosine y back in for the u, we'll have cosine of y equals negative 1. So, when is cosine negative 1? It is right here at pi. Alright, and we're just looking on the interval from 0 to pi. Oh, we're not including pi in our answer. So is there an answer for when cosine of y equals negative 1 within our given interval? And the answer is no, there's no solution. No solution in the interval that we were given. Kind of sneaky there, gotta watch out for those intervals. Alright, now let's use example 9. Or let's take a look at example 9. Use a calculator to find all solutions on the interval 0 to 8 and sketch the graph. So once again, there will be a video for this on using the calculator, but I'll go ahead and get you set up. So for the graphing, you're going to go ahead and split the sides as usual, like we did with that other example in 6.4. You'll have y sub 1 equals, and we can just go ahead and do 2 cosine to the x power, and then let your y sub 2 equal tangent x. And then for your window, we're going to think about our scale here. We want x to go from 0 to 8. So your x minimum, we should let that equal to 0. And then your x max, we'll let that equal to 8. And then your x scale, you can let that equal to 1. Y minimum, we might need to change this, but for now, let's go ahead and just choose 8 for our y minimum. And then for our y max, we'll go ahead and choose 8. So it should be a negative 8 for the y minimum. And then for the y scale, we'll go ahead and choose 1. You might need to change it if you want, but I found this window works well for graphing. So when we went ahead and graphed, our graph ended up looking something like this. Once again, I will upload this calculator work. So the first one, this value here, comes out looking something like this. Second one tangent x is, as you know, what tangent x looks like. And it goes on something like this. Once again, just a sketch of the graph. Now, what we need to do is to trace the values for each of these. So you're going to follow the same directions before, which is when you go to second trace, and then you pick your values and follow the directions for finding each of these points here. And when you do that on your calculator, like we did previously on these examples, x is going to be equal to approximately 0.98, x is going to be approximately 3.64, and x is going to be approximately 7.26. Once again, I will upload a video for using the calculator for this example. And that is it for this section, and those are the practice problems which will be uploaded by the end of the week. Okay, so that's the end of the section. If you need any help with any of the problems or any of the homework, please feel free to email me for an office hour.